Let's state this criterion. Theorem 1218. And the setting is again similar to what we had before, so that U be open in Rn. Again, M and N are arbitrary natural numbers. And we have a map from U to Rm. And we have a point A in U. Now, the first thing we assume, if f is partially differentiable, okay, and here not only partially differentiable in A, but just partially differentiable means in every point of U. And if the partial derivatives DIF, so these are maps from U to Rm, if they are continuous, sorry, I just made a little mistake in stating the theorem, so we'll try. So the maps are partially differentiable on all of A, and it's now sufficient that the partial derivatives are continuous in the point A. So in this one point, continuity is not required to be on the whole set. So if this holds, then the map is differentiable in A. And this is now a handy criterion because we've seen before in some examples that the partial derivatives can be computed by our standard derivation rules, and that usually you see, or you can really tell if they are continuous or not, because we know a lot about continuity now and so on. So if it is just composed of standard continuous functions, it will be continuous. And so this mostly helps us in deciding, so okay, if they look like nice continuous functions, then everything is fine and it's differentiable. Okay, the proof is a bit tedious, and I will be a little bit sloppy in doing this, but let's go through the main idea there. So we start first, assume a particular case, namely the case that M is 1. So we map to, there's a map from U to R. Now, in this case, we can make a little computation, and we can make use of a result from the previous semester, which I hope you still remember, namely the following. So, we need to show that it's a differentiable, so the first thing we need is a candidate for the differential. And we've seen before, so let me scribble this in the corner, this is the last thing, the last corollary we saw, that if D is differentiable, so that dfa of some point V is then the same as the sum from 1 to n di f in A times vi, where these are the components of that point there. Sorry, I just made another little mistake. So if it's differentiable, this formula holds, but if we take a look at this, we know that it's partially differentiable. So this term here on the right-hand side, this is something that's well defined. This is what we can write down. We don't know if differential exists, but this exists. And so since this equation holds, we know if it's differentiable, then this must be the answer. This must be our differential. So the idea is now we define a linear map by this expression here, and then we'll show that this has the property of the differential because this is the only candidate possible. Now, define A as a linear map from Rn to R, which I now write as an element of the dual space again, by the following. A of V is supposed to be the sum I from 1 to n dif times, in A times Vi for all V equal to V1 to Vn as an element of Rn. Okay, this is our candidate. This should be the differential, and so we need to check that it really has the property. So we need to show, and now I formulate the differentiability criterion minimally different. Namely, we have to show that f of A plus h should be f of A plus the differential of f in A evaluated at h, and now plus something which vanishes if divided by the norm of h. So we now do the following. Instead of doing this equation, we just take this difference here. Namely, if we take this difference here in the definition of differentiability, all that's left would be this function phi. So we need to show that this function, so this is now, these are real numbers, so everything I'm doing is well defined. if we divide this by the norm of h, this must be 0. So the limit as h goes to 0 of this expression here is 0, and then we can also take absolute values to show it's 0. So we could put absolute values behind this. This is a real number. So here and here absolute values, but as we have the norm already here, it suffices to put absolute values here and there, and we need to show that this is 0. Okay, this is the main idea here. Now, that we first consider some point h and fix it. So let h be h1 to hn in Rn. Sorry again, I made another mistake. Somehow I'm not in the flow, it seems. We define a sequence of points now in the following way. So here we consider these 2 points a and a plus h. And the idea is now that we want to find a sequence of points between these. Namely, we first define a0 as a. And then, given some aj minus 1, we define recursively. aj is defined to be aj minus 1 plus t times, not t, plus hj times ej for all j between 1 and n. So this means, if we take a look at this recursive procedure, that in aj we have just added the corresponding part of h. So we've added the components of hj in the first j entries. The rest, so the first j entries are the ones from a plus h, and the remaining entries are those from a. So this is kind of somehow interpolating between them. In particular, this means that an, so the final one, is a plus h. So that this is a result of this. Now, what about these terms? So here we make use, we need to introduce a little more formalism. And first of all, the idea is we take a look at this difference, f of h plus j minus f of a, with respect to these points. So this is now f of an minus f of a0. But expressions like this can now be written as a telescopic sum. This is the same as the sum of all j from 1 to n of f of aj minus f of aj minus 1. Okay, sorry, one thing I forgot to mention. So let me just put this in parentheses here. For small h, can achieve that all these points, a1 to a0 to an, are all included in U. This is of course not self-understood, but this is something which you can argue. I have to do a little bit of hand-waving here, but trust me, since U is an open set and we can find some nice ball around this, we can kind of choose H in that ball, and then all these points will be in that ball as well. But this don't bother too much about the details. So here we've just established this as some as this telescopic sum here. And if we take a look at these two summands, they just differ in the jth entry, because here we have added something in the jth entry and here we have not, while all other entries coincide. So this is something where only the jth thing happens. And the idea is now that to express this difference, or to estimate this difference, we can use the jth partial derivative, because that's kind of the only component affected. And for this we need to introduce some little formalism and a nice trick from calculus, from mathematics 1. So for each 1, 2 to n, we introduce an interval called ij. We put ij to be either it is, now just for formal reasons we need to make this distinction, either we take 0 to hj if hj is non-negative, otherwise this is the empty set of course, and if it's negative we just do it the other way, we have to take the other way around, we have to take the interval from hj to 0 if hj is negative. Okay. Sorry, I don't know what's wrong today. Somehow I'm making more mistakes than usual, but anyway. So with this interval, we define now a map which is defined on this interval, namely gj from ij to r, and gj of t is defined as f of aj minus 1 plus t times ej. Okay, so first of all, we observe that Gj of 0, first of all, the first thing I need to mention, this is well defined if we choose small h. So let me, well defined for small h, here I'm a bit sloppy again, because this means if we know that these aj are included, and here it turns out if t is hj, then we get aj, and if t is 0, as I mentioned here already, it's just f of aj minus 1. So the other thing I just said, gj at the other end of the interval of hj is f of aj. This is precisely how aj is defined. And of course, you need to check that kind of if t is somewhere between these values, that this point here is again in u, otherwise this wouldn't be well defined. But this is something I will also not check in detail here, just trust me that for good h, this is fine. Okay, so this is now a map between these 2 points. So this difference here could be expressed, so each of these differences here could be expressed in terms of the Gj. And this is what we will use, but first note something else on the Gj, namely, if we take a look at their structure. So here we only have the Ej component multiplied by t, where t is our variable. This looks a lot like how partial derivatives are defined. And if you take a closer look there, then since f is partially differentiable, each of the Gj is again differentiable. And a little computation shows the following. It shows that Gj prime of t is just the partial derivative djf at that point. So this would be aj minus 1 plus t times aj. And this holds for all t in ij, so in this definition interval. So this is what we get there. Now, the trick is now that we have this function, this is just a map from from an interval to the real numbers. So we can use our knowledge about differentiability of real functions. So we can just use a nice little statement from mathematics 1. And this is what we will do now. Namely, by the mean value theorem, look at our old friend, for differentiable functions. So this was theorem 4.20. By the mean value theorem, there exists some value in the interval, so some tj in ij. Sorry, I cleaned the blackboard here, but I didn't dry it up afterwards. So sorry about that. I hope it's still readable. There is some tj in ij such that the difference gj of hj, and we think now for a moment that we have the interval to be 0 hj and not the other way around, then gj of hj minus gj of 0 is g prime of tj times hj minus 0. Okay, this holds now if the interval is 0 to hj. If it's the other way around, if hj is negative and we have hj 0 as the interval, this would flip signs and this would flip signs. So on both sides, so this equation is still fine for the other case as well. So this always holds. This is just the mean value theorem, and if we now include the definitions here, this means here we've seen that this is f of aj, this is f of aj minus 1, and this is the partial derivative djf at a point which I shall call cj times, and this is just hj, where cj is now defined to be this point aj minus 1 plus tj times aj for each j. Okay, so we have this difference here expressed as partial derivative times a component of the h. And if we now insert this in this telescopic sum here, this is what we use this for. This implies that if we do the following, so wait, I think I'll do both steps simultaneously. Yeah, let me do that. So what we need to check, so again, if you forgot meanwhile, here we are again. So this must be, I made a mistake here as well. This is not the differential because we don't know that the differential exists. This was just the map A that we had just constructed. I'm sorry about that. And we want to show that this has the properties of a differential. Now, we need to show this. And so, first of all, we need to study this. We want to study this numerator here individually. And there we see that this difference occurs that I used here, that is tried as the telescopic sum. So this here minus that is the telescopic sum minus that. And for that we had the explicit formula here. Okay, to put a long story short, f of a plus j minus f of a minus a of h to the absolute value. This is now the sum over all from j equals 1 to n of f of aj minus f of aj minus 1 minus a, and a is defined by that expression. Okay, I switched the index to j as well, so sum from j equals 1 to n dj f in a times hj. Okay, so this was what we had formulated here by the mean value theorem and so on. So this is the same as the sum, the absolute value of the sum from 1 to n djf in the point cj minus times hj minus the sum from j to n from 1 to n djf of a times hj. Okay, and now let's reorder these terms a bit because we can just make one sum out of them and put the hj in the back. So this would be the same as the absolute value of the sum from 1 to n, and now we have dj f of cj minus dj f of a times hj, and since these are this is just some additional, keep it at that, sorry, this is that. Now we know that the absolute value of a sum is bounded from below by the sum of the absolute values. So this is the smaller than or equal to the sum from 1 to n, and now here we have dj f of cj minus the dj f of a, and since this is a product, we can just take it as a product of two absolute values times hj. And here we have already seen before that the absolute value of some component of the vector is always smaller than or equal to the Euclidean norm of that vector. So this is smaller than or equal to, that's the thing I want to squeeze in here, j from 1 to n, dj cj minus f cj minus dj f a times the Euclidean norm of h. Okay, so this is an estimate. We have shown that this difference is smaller than that, and after erasing I will use this then to finally prove this theorem for this case of m equal to 1, and then I will also argue about the general case. So let's insert the previous inequality now into the limit that we need to study. Namely, we need to discuss the limit as h goes to 0 of this absolute value that we just had, f of a plus h minus f of a minus a of h, absolute value divided by the norm of h. Okay, this is then smaller than or equal to the limit as h goes to 0 of, so there we had, the sum, the sum from 1 to n, djf in this point cj, which depends on h, minus djf in a to the absolute value times the norm of h divided by the norm of h. And so, of course, we see these two norms cancel each other out. And we have a sum there, so this is the same as the sum of the limits h goes to 0, sum over all j from 1 to n over the limits as h goes to 0 of dj f cj minus dj f of a. Okay, and now these cj, they depend on h, of course. The cj depend on h, just by construction. But one can see now that, but one checks that if h goes to 0, and here now I'm a bit sloppy, so if h goes to 0, then all these cj, they were defined from, just as the difference from a was just given in terms of h. So they were a plus something depending on h. And if this something is getting small, we're getting more and more towards h. So if this goes towards 0, then cj tends towards a for all 1 to n. So this is just very sloppy and not real mathematics. So probably like all your physics lectures, sorry. But let me keep it at that. So of course I would need to make a big fuss out of it otherwise. So they go to A. So now you can see where we're going, because now we really use the continuity. We have assumed, and that was the key there, that the partial derivatives are continuous in A. So since the djf are continuous in A, it follows that these differences here must go to 0. So it follows that this goes to 0, and this was non-negative, so it's bounded from below by 0. So by squeezing argument, this term from as h goes to 0 of this f of a plus h minus f of a minus a of h divided by the norm of h, that this limit is indeed 0. Okay, so this is 0. This means, that we have shown what we wanted. So f is differentiable in A, and its differential is just this map A. Okay, this is what we've shown. Now, this was the case of m equal to 1, so that we have a function which really maps to r and not to r to the m for some arbitrary m. And so for m bigger than 1, we still need to establish some argument. So this means f is of the form f1 to fm, where fi is a map from u to r for all I between 1 and m. So if we have this situation, we observe that the partial derivative of f, let's keep it as a function, the derivative of f, we have seen that the partial derivatives are given as derivatives of curves, and we've seen derivatives of curves can be taken component-wise. So if we just take a close look, this means that the partial, let's keep some point in there, dif of x, that this is the same as dif1 of x, and so on to dif(m) of x, fm of x. Now these entries here are real numbers, so in the end we get an entry vector in Rm. So this means if the partial derivatives are continuous, so if this is continuous in A, then this means that all of these are continuous. We've seen that a function to Rm is component-wise, is continuous if and only if the components are all continuous. So difj is continuous in A for all I between 1 and n, and all j between 1 and m. So So all of these are functions which map to R with continuous partial derivatives. So this is the case we just studied. So from the case from m equals 1, get that all of these maps are differentiable, so that fj is differentiable in A for all j between 1 and m. But we've seen before in the theorem, and that was Theorem 1214, that some map is differentiable in a point if and only if all the component functions are differentiable in that point. So having this, it follows from Theorem 1214 that f is differentiable in A. And this is finally precisely what we wanted to show. Okay, let's study some example. Namely, let's study a function that we've already, or a map that we have already seen before, namely whose partial derivatives we have already computed, namely example 1219. So f from R2 to R2, f of x1, x2 is e to the minus x1 squared minus x2 squared in the first component and sine of x1, x2 in the second component. So here we've seen that this is partially differentiable and we have computed the derivatives. So by example that was 12.92 where we already treated this one, we have that this is partially differentiable, and we have seen that the partial derivatives can be written down explicitly. This is the first is minus 2x1 e to the minus x1 squared minus x2 squared, deriving this by x1 only, and there we have x2 cosine of x1 x2, and in the second component, for the second partial derivative, we have basically the same with the rows of the variables reversed. Minus 2x2 e to the minus x1 squared minus x2 squared, and here x1 cosine x1 x2. Okay, now both maps are continuous because we can easily see that these expressions here are all continuous and compositions of continuous maps. So here we just have a polynomial and two variables here as well, and the other functions included are just cosine, exponential, and so on. They're all continuous, as we well know. So both d1f and d2f are continuous everywhere, which implies that f is differentiable everywhere. So f is differentiable in every x1, x2 in R2. And we have the formula for the differential with df in a point x1, x2 evaluated at some vector v, and I immediately write this as v1, v2 in R2. So we had this formula with the sum of the partial derivatives. And in this case, where we have only two components here, this means we take the first partial derivative, d1f in x1, x2 times v1, plus the second partial derivative, d2f in x1, x2 times v2. Again, these derivatives are vectors, these are scalars, so we just multiply the components there. So, just writing down with the results we had, this is so minus 2x1 e to the minus x1 squared minus x2 squared v1, and then v1 x2 cosine x1 x2 times v1. And plus now the same for this expression here. There we have minus 2x2 e to the minus x1 squared minus x2 squared v2. And in the second component, x1 times cosine of x1 x2. Okay, and now this, of course, this is just the sum of two vectors in R2. So let's put this together. So we get, just to have the whole thing here, df x1 x2 of v1 v2, if we now sum up and summarize the terms a bit, so just taking constant factors out of there, we get that first we have minus 2e to the minus x1 squared minus x2 squared, and then here we have x1 v1, here we have x2 v1, so x1 v1, x1 v1, and here we have x2 v2, plus x2 v2, so the minus sign went in front here, and in the second component we also see that there's just, here's a v2 missing. So here in both terms we have the cosine of x1, x2, and then here we have x2 v1, and here we have x1 v2, so x2 v1 plus x1 v2. So this is really, and this is something you can check now, and this is not too hard to see, this is really linear in terms of, in v1 and v2, so in this vector here. So this is the way we can kind of really explicitly write down some differential, and of course by the same method we could determine the differential of almost everything, where we can just write down the partial derivatives in that way, and which is kind of composed of nice functions. So this is something you can compute, and you will have opportunities to do this in the exercises, for example. Okay. Then secondly, that's more a remark than an example, the converse of the previous theorem, so of theorem 1218, is false in general. Meaning there exist differentiable maps whose partial derivatives are not continuous. Whose partial derivatives are not continuous. So a very simple example, which is just a very special case, namely a one-dimensional example. Of course, in all of what we did, we could have chosen n equals 1, and then would basically get the same results back that we knew already for derivatives in one variable. So here, in this case, we have f from R to R. F of x is either x squared times the sine of 1 over x. So if x is non-zero, or 0 if x is 0. So, and here one checks, and this is what I will not do. F is differentiable, but the partial derivatives, so there is only one partial derivative, there's only one direction. So d1f, which is simply by definition of the partial derivatives and by this one-dimensional setting, this is just the derivative. So in this case, this is just f prime. If f is differential, but, I wanted to write, sorry, but this map is not continuous. There you can see, if you compute the derivative there, that you get some expression which is not convergent if we go towards 0 with x. Now, this is not continuous, so this is the counterexample. Let me not go into detail on that. Okay, let me erase one last time, and then we have one more corollary and one particular remark which summarizes some of the arguments of this section. One comforting corollary from the previous theorem, namely our favorite class of functions is now differentiable, as we can establish, namely polynomials. Every polynomial in multiple variables, so P from Rn to R is differentiable. And this is good, because these are kind of the most elementary kinds of functions, and if they were not differentiable, it would be a really bad notion of differentiability. So this is good. And this can now be easily derived from the theorem, because as it's easy to see, if we have some polynomial, just by definition of polynomials, obviously polynomials are partially differentiable. So obviously polynomials are partially differentiable. So the derivatives, the partial derivatives of a polynomial are again polynomials, obviously, just by what we know about this, because partial derivatives are built by one-dimensional differentiation, and this is just by deriving polynomials in one variable, so we get back polynomials. If this is not clear to you, please try to recover this argument by yourself and write down for yourself, because this is kind of important and very instructive to see. So the partial derivatives are again polynomials. And this means that they are continuous, because we have proven that every polynomial is continuous. So by the previous theorem, so theorem 1218, this implies P is differential, so polynomials are differentiable. So they are partially differentiable and the partial derivatives are continuous, and so we have it, are differentiable. Okay, great. This is what we know, so our favorite functions are differentiable. And now, instead of doing something new, I just want to summarize what we did here and summarize the different notions of differentiability in the form of a remark. So let U in Rn be open, F from U to Rm, A in U. So what have we seen in this section, or this and the previous things? We just want to order the different notions of differentiability that we have and to order them basically from strong to weak. So we've seen that the strongest was that if we assume that F is partially differentiable and djf is continuous in A for all j. This is something where in Germany you call this property also continuously partially differentiable. I think in English, in the English word, it's not that English-speaking word is not that common, but anyway. So this is what we've just seen, and there we've seen by theorem 1218. This implies f is differentiable in A. So basically our main notion that we have in A. So this is here the important notion, and there are some which are going there. And in the previous example, we've seen that the converse is false. So this is true by theorem 1218, and this is false by example 1219. Then we've seen, if it's differentiable, then all directional derivatives exist. So this implies that all directional derivatives of f exist in A. But there we've also seen that there are functions where all directional derivatives exist. So this was, I don't have the theorem now at hand. Theorem something, sorry. This is where we saw that the differential, if it's differentiable, then recovers all the directional derivatives. So there we've seen that then all directional derivatives exist, but we have also seen an example of a function for which all directional derivative exists, but the function is not differentiable. So that's the example that we had there, and this was example, have I noted this? 1262. No, for 1216.2, sorry. 16.2. Okay, this does not hold. And then we know, particularly to bring back the term of partial differentiability, if all directional derivatives exist, then in particular the derivatives in the coordinate directions, so by the canonical basis vectors exist. So this implies that f is partially differentiable in A. But we have also seen that there are also counterexamples, and this was example 1262. Namely, there are maps for which the partial derivatives exist, but not all directional derivatives exist. Okay, this is what I want to stop with. This is kind of a hierarchy of differentiability properties. So this is the central one. If it's differentiable, then all directional derivatives exist, then all partial derivatives exist. And the strongest one here that we can derive all others from is that if it's partially differentiable and the partial derivatives are continuous in that point. So then we get, this is kind of the superior criterion to get this, but our central term of differentiability that we will use for theoretical results and so on is this notion here. So all these implications hold, but none of the other ones. We cannot go back in any direction, so for everything, for the other directions we have counterexamples for everything. So there's no equivalence between these notions. Okay, so I hope I didn't confuse you with all these notions of differentiability. Probably I did, because when you see this for the first time, this is hard to grasp everything. It takes a while, I promise you, but then you will finally, somehow you will be able to get it. Okay, this is now about differentiability in general, and so we've now established this notion of derivative, but to really use this in practice we need rules for differentiation and for these differentials. In the same way as we had rules for derivatives in one variable in the previous semester, like product rule, chain rule, and several computational purposes like derivative of the sum is the sum of the derivatives and so on. All these things we also need now for differentials here in this higher dimensional setting, and we will establish that in the next section. Especially the product rule and also the chain rule, they have analogs there, and also maybe it's not obvious at this point how they will look like, but they have an interesting form and you can do really beautiful computations with that, which we will do in the next section, and where we'll also learn a bit more interesting and important results about derivatives for going on with that. See you in the next section.